Are you ready to witness science in action and learn how to turn oxygen into drinkable water? Imagine having the power to create clean, refreshing water from the very air we breathe. Get ready to embark on an extraordinary journey as we delve into the fascinating world of oxygen-to-water conversion. Water, as we all know, is the elixir of life, an essential resource without which no organism on Earth can survive. Yet, millions around the globe still lack access to safe and clean drinking water. But fear not, because scientists and researchers are tirelessly exploring groundbreaking methods to change this narrative. They're harnessing the power of chemistry and ingenuity to unlock new pathways to sustainable water generation. Today, we're shining a spotlight on one such innovative approach, the conversion of oxygen, abundantly present in our atmosphere, into pure, drinkable water. Join us as we unravel the science behind this transformative process and discover how it holds the potential to revolutionize the way we think about water scarcity and sustainability. So, buckle up, folks, because this is going to be one exhilarating ride through the realms of science and possibility. Understanding the science behind water conversion starts with appreciating the fundamental composition of water, H2O. At its core, water is a simple yet miraculous molecule, consisting of two hydrogen atoms bonded to a single oxygen atom. This unique arrangement gives water its remarkable properties, making it an indispensable substance for life as we know it. From facilitating cellular processes to regulating body temperature and supporting ecosystems, water plays a crucial role in sustaining all forms of life on our planet. Now let's turn our attention to the vast reservoir of oxygen that envelops our planet, the Earth's atmosphere. Oxygen constitutes approximately 21% of the Earth's atmosphere, making it the second most abundant gas after nitrogen. This abundance of oxygen presents an intriguing opportunity for scientists to explore its potential for conversion into water. By tapping into this vast resource, researchers aim to develop innovative methods that could help alleviate water scarcity and ensure access to clean drinking water for communities worldwide. Indeed, the notion of harnessing atmospheric oxygen to produce water may seem like something out of a science fiction novel, but the underlying principles are firmly rooted in scientific reality. Through a combination of chemical reactions, physical processes, and ingenious engineering, scientists are unlocking the latent potential of oxygen as a source of fresh water. From electrolysis to combustion and chemical reactions, a myriad of approaches are being explored to convert oxygen molecules into the life-sustaining liquid we all depend on. One of the most well-known methods is electrolysis, a process that involves passing an electric current through water to break it down into its constituent elements, hydrogen and oxygen. This separation occurs at the electrodes, where water molecules undergo a reaction, yielding hydrogen gas at the cathode and oxygen gas at the anode. By carefully controlling the conditions, researchers can collect and store the produced oxygen, which can then be combined with hydrogen or other elements to form water molecules. Another intriguing approach is combustion, where oxygen is utilized as a reactant in chemical reactions to produce water vapor. During combustion, substances undergo rapid oxidation in the presence of oxygen, releasing heat and generating water vapor as a byproduct. While combustion processes are commonly associated with energy production, researchers are exploring ways to harness this principle for water generation, particularly in environments where other methods may be impractical. Beyond electrolysis and combustion, scientists are exploring a diverse array of chemical reactions to convert oxygen into water. These reactions often involve the combination of oxygen with other elements or compounds to form water molecules. By leveraging the principles of chemistry, researchers are uncovering novel pathways for water production, paving the way for innovative solutions to address water scarcity challenges. Each of these methods presents unique advantages and challenges, and researchers continue to refine and optimize their approaches to maximize efficiency and sustainability. Whether it's through electrolysis, combustion, or chemical reactions, the quest to convert oxygen into drinkable water represents a testament to human ingenuity and our relentless pursuit of solutions to pressing global issues. Electrolysis is a chemical process that involves the decomposition of a substance through the application of an electric current. When applied to water, electrolysis causes the water molecules to split into their constituent elements, hydrogen and oxygen. This separation occurs at electrodes submerged in the water, known as the cathode and anode. At the cathode, hydrogen ions, H+, in the water attract electrons from the cathode, forming hydrogen gas, H2. Meanwhile, at the anode, water molecules lose electrons and release oxygen gas, O2. The result is the production of hydrogen gas at the cathode and oxygen gas at the anode. By carefully controlling the flow of electricity and the conditions within the electrolysis chamber, scientists can efficiently separate water into its component gases. Once collected, the hydrogen gas produced through electrolysis holds tremendous potential as a clean and renewable fuel source. Hydrogen can be used in fuel cells to generate electricity, powering vehicles, homes, and industries with zero emissions other than water vapor.
While hydrogen often steals the spotlight in discussions about electrolysis, oxygen is equally valuable. In fact, the oxygen produced can be harnessed to address water scarcity by combining it with hydrogen or other elements to form water molecules. By closing the loop and utilizing both gases produced through electrolysis, researchers are exploring innovative approaches to sustainable water generation, offering hope for a future where clean water is abundant for all. In combustion processes, oxygen serves as a crucial reactant in chemical reactions, often combining with other substances to produce heat, light, and various byproducts, including water vapor. When a fuel undergoes combustion in the presence of oxygen, such as in a flame or combustion chamber, the fuel molecules react with oxygen molecules to release energy and form new compounds. For example, in the combustion of hydrocarbons like methane, CH4, oxygen, O2, reacts with methane to produce carbon dioxide, CO2, and water vapor, H2O, CH4, G plus 2O2, G, CO2, G plus 2H2O, G. As the reaction proceeds, water vapor is released into the atmosphere, contributing to the overall moisture content. In certain applications, particularly in controlled environments or industrial processes, combustion can be harnessed to generate water vapor intentionally. However, while combustion-based water production offers potential benefits, it also presents several challenges and limitations. One significant concern is energy efficiency. Combustion processes typically require a significant input of energy to initiate and sustain the reaction, often resulting in inefficiencies and energy losses. This can lead to increased energy consumption and costs associated with water production, limiting the scalability and practicality of combustion-based approaches. Furthermore, combustion processes can generate byproducts such as carbon dioxide, CO2, and other pollutants, depending on the type of fuel and combustion conditions. The release of these pollutants into the atmosphere can contribute to air pollution, climate change, and other environmental impacts. As a result, mitigating the environmental footprint of combustion-based water production methods is essential to ensure sustainability and minimize negative consequences for ecosystems and human health. Despite these challenges, ongoing research and development efforts are focused on optimizing combustion processes for water production, exploring alternative fuels, improving energy efficiency, and mitigating environmental impacts. By addressing these challenges, combustion-based approaches have the potential to play a role in sustainable water generation, complementing other methods and contributing to a more diversified approach to addressing global water scarcity.
Chemical reactions offer a diverse array of pathways for generating water molecules by combining oxygen with other compounds. One common example is the synthesis of water through the reaction between hydrogen gas, H2, and oxygen gas, O2, commonly known as the combustion of hydrogen. This reaction produces water vapor, H2O, as a byproduct. Similarly, various chemical processes involving the oxidation of hydrogen-containing compounds, such as alcohols or hydrocarbons, can yield water as a product. For instance, the combustion of ethanol, C2H5OH, in the presence of oxygen produces carbon dioxide, CO2, and water vapor. Additionally, certain chemical reactions involve the direct combination of oxygen with other elements to form water molecules. Feasibility and practical applications of these reactions for water generation depend on various factors, including the availability of reactants, reaction conditions, and energy requirements. In practical terms, the feasibility of utilizing chemical reactions for water generation depends on factors such as scalability, cost-effectiveness, and environmental impact. Some chemical processes may be suitable for small-scale applications or specialized industries, while others may offer potential for large-scale water production. For example, certain industries, such as pharmaceuticals or electronics manufacturing, may utilize chemical processes to generate water as a byproduct of other manufacturing processes. Additionally, researchers are exploring innovative chemical reactions for water purification and desalination, offering potential solutions for addressing water scarcity in coastal regions or arid environments. Overall, chemical reactions represent a versatile and promising approach to water generation, offering opportunities for innovation and sustainability. By leveraging the principles of chemistry and engineering, researchers continue to explore novel pathways for harnessing oxygen and other compounds to produce clean, drinkable water, contributing to efforts to ensure access to safe and sustainable water sources for all. One of the most exciting applications of oxygen-to-water conversion technologies lies in space exploration. In space, where resources are limited and precious, the ability to produce water from oxygen becomes paramount for sustaining life. Systems such as electrolysis units aboard spacecraft enable astronauts to generate water by extracting oxygen from sources such as water ice or recycled breath moisture. This self-sufficiency in water production is crucial for long-duration space missions, enabling astronauts to stay hydrated and supporting various life support systems. Furthermore, oxygen-to-water conversion technologies hold immense potential for sustainable living here on Earth. In regions facing water scarcity or contamination, such technologies offer a viable solution for accessing clean drinking water. By harnessing abundant resources such as atmospheric oxygen or renewable energy sources, communities can implement decentralized water generation systems, reducing reliance on centralized water infrastructure and mitigating the impacts of droughts and water shortages. As research in this field continues to advance, scientists and engineers are exploring innovative approaches to improve the efficiency, scalability, and sustainability of oxygen-to-water conversion technologies. For example, advancements in electrolysis technology are leading to more efficient and compact systems capable of operating in diverse environments, from remote off-grid locations to urban settings. Additionally, research into novel catalyst materials and reaction pathways holds promise for enhancing the performance and durability of water generation systems while reducing energy consumption and environmental impacts. Moreover, ongoing efforts are focused on addressing scalability challenges to enable the widespread adoption of oxygen-to-water conversion technologies. By optimizing manufacturing processes, reducing costs, and streamlining deployment and maintenance procedures, researchers aim to make these technologies accessible and affordable for communities around the world. Collaborative initiatives involving governments, academia, and industry stakeholders are driving progress in standardizing and scaling up water generation solutions, paving the way for a future where clean, drinkable water is available to all, regardless of geographic location or socioeconomic status. In summary, the practical applications and future prospects of oxygen-to-water conversion technologies are vast and multifaceted, encompassing space exploration, sustainable living, and humanitarian efforts. With ongoing research and advancements, these technologies hold the promise of revolutionizing water access and security, shaping a more resilient and water-secure future for generations to come. Let's now address safety considerations and environmental impact, crucial aspects of oxygen-to-water conversion technologies that warrant careful attention. First and foremost, safety protocols are paramount when working with oxygen and chemical reactions. Oxygen, while vital for life, can also pose significant safety risks if mishandled. Oxygen supports combustion, making it highly flammable and potentially hazardous in certain conditions. Therefore, it's essential to follow strict safety guidelines and protocols when working with oxygen, including proper storage, handling, and ventilation measures to minimize the risk of fire or explosion. Similarly, chemical reactions involved in water conversion methods require careful handling and supervision to ensure the safety of personnel and the surrounding environment. Many chemical compounds used in these reactions may be toxic, corrosive, or reactive, presenting potential health hazards if not managed properly. Therefore, researchers and practitioners must adhere to established safety protocols, such as wearing appropriate personal protective equipment, PPE, working in well-ventilated areas, and implementing spill containment measures to prevent accidents and minimize exposure risks. In addition to safety considerations, it's essential to address the environmental impact of water conversion methods and mitigate any associated risks. While the goal of these technologies is to provide access to clean drinking water, their implementation must be mindful of potential environmental consequences, such as energy consumption, waste generation, and ecosystem impacts. For example, certain water conversion methods may require significant energy inputs, contributing to greenhouse gas emissions and air pollution if derived from fossil fuels. To mitigate these risks, researchers are exploring renewable energy sources such as solar or wind power to power water generation systems, reducing their carbon footprint and environmental impact. Furthermore, the disposal of waste products or byproducts generated during water conversion processes must be managed responsibly to prevent contamination of soil, water bodies, or air. Researchers are developing innovative waste treatment and recycling methods to minimize waste generation and maximize resource recovery, promoting sustainability and environmental stewardship. Overall, by prioritizing safety protocols and addressing environmental concerns, researchers and practitioners can ensure that oxygen-to-water conversion technologies contribute to sustainable water access while minimizing risks to human health and the environment. Through ongoing research, innovation, and collaboration, we can advance towards a future where clean, safe drinking water is available to all, in harmony with nature.
Experiment time. Wear safety goggles and gloves throughout the experiment. Work in a well-ventilated area to avoid inhaling fumes. Prepare the bottle. Clean the bottle thoroughly and ensure it is dry. Using the funnel, add a small amount of manganese dioxide into the bottle. Securely close the lid of the bottle, adding hydrogen peroxide. Pour hydrogen peroxide into the bottle, filling it about 1/3 full. Be cautious not to spill or splash the hydrogen peroxide. Initiating the reaction, gently swirl the bottle to mix the hydrogen peroxide and manganese dioxide. As the reaction begins, oxygen gas will be produced. Collecting water. Allow the reaction to continue for several minutes. Place the bottle in a cool area, such as a refrigerator or ice bath, to encourage condensation. After some time, droplets of water will form on the inner surface of the bottle. Harvesting drinkable water. Carefully open the lid of the bottle to avoid disturbing the setup. Using a clean dropper or syringe, collect the condensed water droplets. Transfer the collected water into a clean container for drinking. In this experiment, we utilized manganese dioxide as a catalyst to facilitate the decomposition of hydrogen peroxide, H2O2, into water, H2O, and oxygen, O2. The manganese dioxide provided a surface for the decomposition reaction to occur more rapidly, allowing us to observe the production of oxygen gas bubbles. Additionally, by placing the bottle containing the reaction mixture in a cool environment, such as a refrigerator, we encouraged the condensation of atmospheric moisture on the inner surface of the bottle. This condensed water vapor, combined with the collected oxygen, resulted in the formation of drinkable water droplets. In conclusion, we've explored the fascinating process of converting oxygen into drinkable water through a simple yet effective experiment. By utilizing manganese dioxide as a catalyst and harnessing the power of chemistry, we've demonstrated how readily available materials can be used to generate clean, potable water from the air we breathe. We encourage all our viewers to try this experiment at home and share their results with us. It's a fantastic way to learn about basic chemical processes while also gaining a deeper appreciation for the importance of water and sustainability. Remember, safety always comes first. Dispose of any leftover chemicals properly and clean up your workspace thoroughly after conducting the experiment. Always wear appropriate safety gear and follow safety guidelines when working with chemicals. If you enjoyed this experiment and want to see more DIY science content, don't forget to subscribe to our channel. We'd love to hear about your own experiments and discoveries, so be sure to share your experiences and results in the comments section below. Thanks for watching, and until next time, stay curious. Subscribe for more videos like this.